Okay, good afternoon again, everyone. So, without further ado, I'm very pleased to hand over to Iain Miller from Northern Power Grid, who will give us a distribution network perspective on some of these issues. Iain.
Thank you. That definitely sounds like I'm mic'd up. I can hear myself coming back in my own ears. It's lovely to be on at the end of the day. It's just a bit of pity I haven't heard everything that everybody else has had to say. Unfortunately, I was down in London this morning on a DSO event, having explained, a stakeholder event, where people were explaining to us why we're not active enough and not doing enough and not listening to people enough and all sorts of good things like that. So I'm fully expected to be told at some point during this that I don't know any maths, which, to be fair, probably won't be far off. So the future energy system challenges from the point of a distribution company, and you catch us in transition, I think. You catch us when we are a distribution network operator, distribution network owner, perhaps, moving to being a distribution system operator. What's the difference? It's a spectrum. At one end, you have a completely passive system that has no active components in it whatsoever, and that's a network owner, and they don't really exist. We've always had some level of active componentry in there. And at the other end, you have something where everything is active, it's dynamic, it's reconfiguring itself automatically all the time, either autonomously or with the input of people. And that probably isn't practical at the lowest voltages either. So there's a spectrum with those kind of bookends, and we're somewhere in the middle towards the network owner end, moving towards a more active system operator. The fundamental challenges, though, remain exactly the same. Put simply, get them on, keep them on, and if they go off, get them back on. So that's connections. And then I'm going to call it asset management for the moment, but I might just come back to that. And then it's repairs and restoration. So that's the three things that we're providing essentially as an essential service. And can we do it cheaply, safely, timely? And instead of customer service, I put politely there. Customer servicely doesn't make sense. So why did I say I want to come back to asset management? That's in some ways the most interesting one. Yes, all the things that are going on will change the connections process and the repairs and restoration process. But that bit in the middle, keeping them on, that's where the difference between network owner and system operator starts to come into its own. Because that's about understanding you've got an active user on your network. Sometimes they're generating, sometimes they're consuming, sometimes they're taking into storage, sometimes they're pushing out of storage. Sometimes they've decided that yes, they're going to take load off your system, but they're going to do it at a certain time of day in response to some tariff or other. And sometimes they're doing exactly what they do now and just acting essentially passively. And that's probably where the biggest change is happening. But fundamentally, the challenge for us is still the same. So why are people talking about it? The difference, I guess, and I've alluded to it in there already with the EVs, one of the few big forms of load, and big to us at least. 3 kilowatts might not look too huge to NGC, I think they're in the room as well somewhere else. But for us, that's a reasonably big load at a domestic level. One of the few that the only thing I can definitely tell you about it is the time that somebody comes to use it, it's not going to take any power. That's unusual, particularly given they only use it 4 hours a day. Now you can say the same about your electric toothbrush and maybe a cordless drill as well, but they're not 3 kilowatts. So this is something that might have 40 kilowatt hours of storage in it. It might be 3 kilowatts, might these days be 7 or even 10 kilowatts domestically. Certainly a small business type place. That actually, you can move that around. So it's in use 4 hours a day, say. There's 20 hours that can refill it. It only uses 10 kilowatt hours a day on average. Some people who've driven here today, if they've got an electric vehicle, might have used loads more than that. But on average, it's 10 kilowatt hours a day. 20 hours, 500 watts. 3 kilowatts, so I can move that around quite a lot. I can play with that. And nobody cares, provided it's still good when they want to drive it again. And there's, in a 2018 Nissan Leaf, 40 kilowatt hours, that's about 4 days driving. So you can play with that. Heat, again, if I were to switch your heating off for 5 minutes on a kind of heat pump into some sort of thermal storage, and remember, a well-designed house is a thermal store, you probably don't care. But that might be enough to slide you by a peak and not burn out a bit of equipment. Storage, well, that kind of speaks for itself, that you can move things around, you can power it up, power it down. And that's at one level. At the other level, if we are going to move to a more renewable future, and we don't seem to be very good at getting nuclear power stations on at the moment, so let's assume that there's going to be more emphasis on things like PV and wind, offshore wind, maybe even tidal. These are things that happen when they happen to some extent, and we'll need some form of storage. Now, tidal, you might have a big lagoon, and that's a great form of storage in some ways. Technically, it's a great form of storage. Ecologically, I'll let somebody else tell me. But with PV, the only real way I can store that is either pump it into the house as heat, either in a thermal store in the house itself, or into a battery, or something like that. So not only is it a flexible form of load, it is actually one of the few solutions to some of the issues coming forwards. New evolving techniques to go alongside those. We are getting better at power electronics and communications. We get more and more all the time. I said there were no active components in a true network operator network. Never been that way. We've always had control of the voltage, and that's always been active. Well, since I can remember anyway. And we have there a lovely system that uses time as its communication system. So you have two levels in it. You control voltage on your 132 to 33 kV point and on your 33 kV to 11 kV point, and you set the time that each of those relays takes to take over, such that you sort a wide area problem first, if there is one, and you sort the local problem second, and that beautifully grades. And last time I checked, you can't hack it, but it's inflexible. It doesn't allow you to trim things the way you'd like to, and to do things with that. Perhaps at times you want to reduce, suppress the voltage to create an effect, or raise the voltage to create another effect. You can't do that. So you're into more power electronics and more comms. Firm and unfirm, we've always had firm and unfirm. This is when you have a supply that normally is good for 10 MVA, but when we have an outage it's only good for 5. Well, that is now migrating into some really far more subtle versions, because 5 or 10, there's your lot, is a bit kind of not quite digital, but it's a bit there. Demand side response and active network management mean that we're actually trimming people's output, or allowing them to trim their output, so they can get cheaper connections and things like that. And that will continue to roll out and become more involved. But it does mean that in certain areas you get some funny effects. That as people's demand reduces, all that happens is other people's demand rises. And that can be really upsetting for NGC amongst others, where they have standby generation, not standby, short-term operating reserve generation store. And when they call on that to operate, it operates fine in line with the contract they've got, and generation comes up. And all that happens is over here, the other 3 generators on that network are told to throttle down so they don't burn out our transformers. And everybody's done everything properly. So you get into some interesting bits and pieces around that. Time of use tariffs, we've always had economy 7. I think I found the original paper on economy 7, 1948. It's actually a very, very good paper, and explains diversified maximum demand better than anything I've ever seen since, in a way that's not patronising, is very understandable and very accurate as well. So if you get a chance to read that, I recommend that to you. It's very much a Whitehall paper, but very, very good. That's my evolving into time use tariffs, where they might be dynamic. It might not be the same time every day. It might move up and down different half hours. It might be different in different parts of the network. Those things are starting to come online. And then, how do we control the network in terms of switching things around? Even when I joined, which is a while back now, back in '92, most of our switching on the 11 kV and below was done by people turning up in a car or a van, getting out, finding a telephone, ringing into control and saying, right, I'm going to do this now, and then switching things around. Prior to that, that'd been the only way of doing it. By the time I'd arrived, the SCADA was there on the 33 kV system and just reaching into the 11 kV system. By the mid to late 90s, we had some level of remote control on our 11 kV system. That's now, not everywhere, but there's a lot of it out there now. And we're now moving from being able to control it remotely to the control systems themselves taking control of faults, with APRS standing for Automated Power Restoration System. So that's the evolution there. And I've chucked cyber in at the bottom there. I get awfully worried about cyber. I've said this many times. I said it this morning, but it's very, very true of the profession I'm in. We are professional worriers, and we're damn good at it. We will worry about everything to the nth degree, and that is why we end up in an uncontrolled environment with reliability that's pushing 4 nines. So 99.99, whatever, that's the kind of level of reliability we're hitting in an uncontrolled environment. You don't get there without having some level of worry. Now, why do I worry about cyber? All this comms, all the power electronics and IT systems, OT systems that have the potential for so much benefit, equally have the potential for becoming a single point failure. If somebody was to break into the control system of a large utility, they can switch everybody off in one go now, and that will continue to be the case. I'm going to show you some projects later on, and one of the projects I'm going to show you starts to address that. Now, large utilities, generally speaking, are aware of that and have good levels of cybersecurity and controls, and they might even have secondary systems that stop that sort of thing happening. But we're now in a chain, I need my fingers at this point, where we have a generator, a transmission company, a distribution company, a retailer, a metering operator, the DCC, an aggregator, the internet-enabled equipment that somebody's bought with a chip from China. All of this is potentially hackable. Some of it more so than others. So that was what, 7 or 8 steps? Anywhere you break into that chain, you can cause havoc. Because by breaking into, you don't even have to get into everybody to switch everybody off. That's the really problematic thing. You can start causing some problems with relatively low levels of penetration. And there is no way that we're going to be able to ever say with hand on heart that all of those are secure. It's not happening. So alongside cybersecurity, I start to get interested in cyber recovery and cyber resilience. Cyber recovery being, right, if somebody breaks in and does something nasty, how do you do the kind of the classic ring up the IT section, right, have you tried switching it off and on again and see if it comes back to you? I've actually been on a plane when they did that. That was interesting. Cyber resilience is, well, the best way that I can describe it is some of you in the room will know exactly what I mean and some of you won't, and my apologies to the ones who won't. but do you remember those 1950s British black and white cops and robbers type film? And there'll always be a scene where the cop jumps on the front of a car and hits the windscreen with his baton, and the thing just crazes into a whole of tiny little pieces. Each of those pieces has broken in such a way that it doesn't cut you. And you can push it out with your hand and continue on. And that's roughly what I mean by cyber resilience. I want the system to break in such a way that it fails at a global level, but not at an individual level for customers. That each piece can continue on. And that is where some of the work we're looking at is going now. But it does rely very much on understanding the balance we have. And when I talked about the change in what keeping people on means, you're then into, can I locally balance things? Can I balance the generation, storage, demand at whatever that level, that fractal level that I've broken the system to is. So areas of interest. We're interested in the extra demand from heat and EV. I'll have a bit of a look at EV in a minute. Heat is a big problem. There's an awful lot of it. When you look at the amount of energy that's consumed, particularly the amount of power that comes from, say, the gas network, when a cold weather front moves in, the ramp up rates, that kind of worries poor electrical engineers like myself. We do get worried about that sort of thing because our system wasn't designed for that. EVs, maybe less so. On the plus side, once we worked out how to connect all that heat and all that EV, it's a time shiftable load. We can do things with that. We can play with that, and that has some real potential for us as network companies. It also has potential if you're a generator though. Imagine it's a windy day and a sunny day and you've got more energy coming in than you can possibly sell. The obvious thing would be to talk to some of your time shiftable customers and say, right, fill your boots now. It's cheap. Use the energy, use the power, get on with it. Well, that's fine, except that the network was designed around some assumptions on diversity. And when you look at the diversity assumptions on the LV network, it's about a 10-to-1 ratio. If you look at all the peak loads that we could have, effectively you add up all the contracted loads at people's houses, it is 10 times what we actually see. If somebody says it's a really good time to buy energy, it's really, really cheap at the moment, we really do run the risk of everybody starting to take what they can at that point. And again, our system wasn't designed for that. Yes, it's not good. It could melt things. We don't like melting things. So there are both pluses and minuses to that whole time shiftable element and the time of use tariffs that might be associated with it and things like that. Along with that, I don't work for an energy company today. I work for a power company. I really couldn't care less how much energy we shift through our network. It makes not a jot of difference to me. What I care about is how many connections are out there that I have to go to and how much peak power I shift to each of those connections and as a whole. Now that's not unrelated to energy, but it's not the same thing. As soon as I start talking about storage and time shiftable loads and things like that, that line becomes blurred. Because if a house wants 10 kilowatt hours for the house and another 10 kilowatt hours for the car, but really doesn't care when it gets them, and by the way it's got a kind of 15 or 18 kilowatt connection, so theoretically it could take it in about an hour and a half, 2 hours, suddenly I have to start worrying about the energy that people want. Flip side is, when you average that house over a 24-hour period, currently it's only doing, say, about 400 watts on average. And we built a system that's good for about 2 kilowatts. So, again, it's all going to be about how we can manage these things and how we can make the numbers add up in the right way. The next step in reliability and resilience, I'll mention more about that on one of the projects. I've got just examples later on. But at the moment, we have got to the stage where we're really good at switching people back on very quickly. And we're getting better and better at that, and you have seen the measures of how reliable we are tumbling. They've gotten better and better. It's about half what it was back in the 90s now. It's probably better than that, but I haven't checked just recently. And that's due to things like the APRS that I mentioned previously, which the computer, as soon as it sees somebody's off supply, goes, I know how to switch these people back on, and it switches them back on. Great, but they still went off in the first place. And that's still only applicable as far down as our 11 kV system, and in some cases 6.6 kV system, but the high voltage system. So the next step is to stop people going off in the first place. Now that will make potentially a big, big difference to rural areas, which see the majority of those short-term faults. It might make a difference to rural economies. It will mean that knowledge work is far easier to do from the back end and beyond, because you can actually rely on all the power that fuels the comms to actually work. Whether you can rely on the comms is another question, but I'm not responsible for that, so that's another guy. And that sort of thing, that's our next step change. How do we stop people going off in the first place? Right, and I'm getting a hurry up. Cybersecurity, cyber resilience, cyber recovery I mentioned, so, and then the whole DNO, DSO thing I mentioned as well. And there is a fundamental question, which is when you don't know what the law is going to do because somebody's going to control it according to time of use type things, how the blazes do we model it? Because it's all modeled on assumptions of statistical behavior that was modeled in the 70s, has been remodeled since through things like CLNR and things like that. But the reality is the techniques are the same. We just assume that people will use it when they want to use it and not when they don't want to use it. And people are fairly predictable in their behavior. Once you start layering control systems on top of that, it becomes less predictable and more difficult to model, certainly for poor individuals like us. Taking EV just as demand, sorry, EV as demand is just an example. We've done a fair amount of modelling from where we are now, kind of around about this level, and we think we're going to end up somewhere in that range in terms of number of electric vehicles. What that actually means, never mind the number of electric vehicles, varies spectacularly depending on where they are, speed of charging, and what sort of functionality is built into the chargers. Yeah, the energy requirement, great. That's basically about how far you drive, but the other three make a huge difference. However, we think we can cope. You start with a kind of base assumption that could give you a 60% rise in peak energy. This is true if you leave people to their own devices. If you can persuade people to charge at work, charge at home, you half it, give or take. The load used to be 15% higher 10 years ago. Our load is falling quite noticeably at the moment. So there's another 15 dropped off. So, and they come over 20, 30 years. So that 15%, that 60% became 15%, and we're going to do it over 20, 30 years. We're talking about less than 1% per annum rise for electric vehicles. And by the way, we do sack loads of asset replacement over that time period, and you never put a smaller asset in if it makes sense to put a bigger asset in, and the cost of putting assets in is in the action, not in the size. Classic one is if you dig a hole for a cable, that's the cost. The cable is virtually free. Actually, it's a reinstatement, but don't worry about that. So we think we're going to take it in terms of charging those vehicles, but coping isn't enough. If I leave and around my retirement do, my boss turns up and says, he's a great lad, he coped. It doesn't feel I've moved the game forwards very much, does it? And I think of all these things that we might be looking at, then it's the fourth one there that is the most interesting thing to me. 30 million vehicles on the road today. Well, it's about 31, 32 actually, but let's call it 30. Nissan Leaf from 2018, 40 kilowatt hour battery. For those of you who are quick at the arithmetic, 1.2 terawatt hours of storage. For those of you who know how much electrical energy moves about the UK system, that's about a day and a half, on average, across a year. Now, disingenuous, because all those vehicles aren't fully charged at any time, and some of them are on the road, and some people want to play and allow you to use their vehicles as storage, and some won't. But either any way you cut it, that's a big number. And if we fail to use that, then really we failed as engineers and we failed as a sector, because that is a huge opportunity there. I do have some examples which I can go through, but I think I'm being called on time, so I'm just going to really quickly go through. V2G, that's about solving the technical challenges of using the batteries in cars to help our network. E4 Future is looking at the commercial issues associated with that. So once you've got the technical thing sorted, you best sort the commercials and find out how much money people want and how much money there is in it and where the value is and who gets that value. GenDrive is trying to do the same thing, and there's a brilliant project. The biggest is based out of GenGain, which was the biggest DSM, DSR project in terms of participants, active participants in the country, with over 2,000, I think about 2,500 actually, but it's of that order. Brilliant, brilliant project. They're now looking at how they can apply that to cars and use social media to get people to actually charge the cars at the right time. I don't believe it works, but it appears to. The numbers are saying it does. It wouldn't get me to do it because I don't do social media very much, but Micro resilience. Let's put some power electronics in and take batteries. Firstly, put a battery there. AC/DC AC converter is what we're going to use. Put the battery in, fullest of time, use V2G to charge it up. We can now have amphibious islands. Sometimes they're on the network, sometimes they're not on the network. Those little microgrids can look after themselves when the HV is gone or when the grid is gone. That is some of the change going forwards. Using the power again, doing the same thing but in a van. That's real. Those are not mock-ups. That van is currently, I think it's currently down Darby Way somewhere at the moment, having a couple of tweaks done to it, but it's real. And then doing the same in a house. The objective here is all these things, once we understand usage better and storage better, we can actually get to a stage where people just don't go off supply, and actually starts to make the higher levels of our system and national grid system less and less of a problem. It shouldn't impact people's lives. I'll leave it there.
Okay, any quick questions for Iain?
Can't promise quick answers.
Yeah, David Slim Shape, David Sonswell. I was just wondering about your comments. As battery storage prices come down, do you fear that you might lose customers because some people in remote locations may just disconnect from the grid altogether, or?
They might. I'm not feeling overly worried about that. I'll tell you why I'm not feeling overly worried about that, and it's a bit of a side story, which is I spent 10 years living in a lovely barn conversion a little bit outside town on a septic tank, which is effectively the sewage version of a battery, isn't it? Trust me, I don't want my electricity supply coming off a battery. I want to be connected. Now, would I like to be in a situation where when the main supply fails, I still have a supply that looks after my house? Absolutely I would. But that microgrid is probably in and of itself less reliable than the mains that currently feed you. Now, somewhere where there is no network now, then the answer, that might well be the answer. And by the way, we might well be interested in putting those in. Not this year, probably not next year, but see us in 5-10 years time, and we might well just be looking at off-grid place and say, tell you what, we'll put your microgrid in until such time as we actually get a network there, and that might be 20 years off, but don't worry about it, we'll look after it in the meantime.
Jan Maciejowski from Cambridge University. How much of the distribution network can carry power bidirectionally, or is that a factor at all?
There are some protection issues on occasion. There are some issues with particular components, and it's the tap changers on certain sorts of transformers, 33 to 11. The cables are fine in both directions. The design can mean that voltage rise can be an issue. Well, there's an easy way to sort that. You just drop the volts. Because remember, we dropped from 240 plus or minus to 230 plus or minus. Guess what all the electricity companies did in response to that? Given that we're still within stat limits? Nothing. So if we wish to actually address that, we can go, and we are doing, I think we've done about 2/3 or 3/4 of our subs so far, dropping the volts by a couple of percent to address the voltage rise issue. Bidirectional is not a problem. I've been putting generation in that was bidirectional. As a design engineer, I was doing it in the late 90s. You know, if you have a decent design engineer, it's just not a problem.
Okay, thank you Iain again.